Watch Mr. Wizard. That's what all the kids in the neighborhood call him, because he shows them the magic and mystery of science in everyday living.
Mr. Wizard.
Oh, hi, Doc. Stay right there. Don't move. Close the door, but stay right there. Because I have a problem for you. I want you to turn on the light, but before you do, I want you to see if you can estimate how long it takes from the time you flick the switch until the light comes on. Well, go ahead, try it once and see if you can tell. How long did it take?
Goes instantaneously, actually.
Seems like it, isn't it? Seems like
right
it's instantaneous. Well, before you leave today, we will be able to time the amount of time that it takes for the light bulb to get up to brilliance after you turn off the switch.
You mean there is an interval?
Right, there is an interval. It's not instantaneous, as you say. There is, in fact, scientists time it all the time. And the instrument that we're going to use to time it with is this one right here.
Oh, that's the oscilloscope, isn't it?
Right, the oscilloscope.
What are those funny designs you have on there?
Well, you'll understand about those later. In fact, you'll be able to make some and, in fact, interpret a lot of things by looking at them. But you knew about an oscilloscope because we've used it before.
Right.
What did we use it for?
We used to show electricity, impulses.
Yes. In fact, we looked at music, didn't we? Saw
Right.
squiggly lines on it. But this is something new. Circles, sort of bouncing circles and baskets and all kinds of things. Well, you'll understand about that later. Right now, I want to see if I can explain why I set up that problem of the light switch. That seems like a kind of nonsensical thing, but it is extremely important because it illustrates the kind of problem that scientists solve. Excuse me, Doug, I want to go around here and see if I can show you now why it's important that we know something about that. You recognize what that thing is?
Looks like a satellite.
And this?
What looks like a radar.
A radar, right. Now, you know, how does radar work?
Well, I think it doesn't send out electrical or, I don't know what kind of...
Radio signal.
Radio signal.
Yeah.
And it goes over here, and then it hits the satellite or the object, and then I think it bounces back. And they measure it.
Measure. Now, the impulses that come out of the radar set travel very fast.
Oh, it's the speed of light.
Yeah. Miles per second. Speed of light. Okay, now, let us say that we can time the interval when the pulse leaves the radar antenna till it goes out until it comes back, and we find that it's 2 seconds.
2 seconds?
How far away is the object?
Well, I guess it has to be 186,000 miles away.
Why?
Well, if it goes in 2 seconds, that means it's going 1 second there and 1 second back.
And in 1 second, it must be that far away.
That's right.
Okay, so you now know that 2 seconds equals 186,000 miles. That's a long distance, isn't it?
Yeah.
Okay, what if it comes back in 1 second?
1 second? I guess it should be half of that.
Half of this, which is what?
93,000.
93,000 miles. How about 1/10 of a second?
1/10?
Yeah.
I guess you'd move the decimal.
Yeah, just take one decimal.
And it'd be 9,300 miles.
9,300. How about 1/100?
1/100? Well,
Take off another one,
930 miles.
930 miles. Now, 1,000.
Well, it'd be 93 miles. Again.
93 miles and 1/10,000.
1/10,000?
Yeah.
It'd be 9.3 miles.
9.3 miles.
Boy, you get such a short interval of time.
Yes, you see, here we're talking about 10,000th of a second. If you are going to do this, you have to have some kind of a measurement of 10,000th of a second, and even 100,000th of a second.
How can I measure that?
Well, the oscilloscope does it. And that's what we're going to use today to time the business about the light bulb. The light bulb lighting up is a long time compared to some of these.
It is?
In fact, well, you know, airplanes flying around the airfield less than a mile away, they're on the radar scope and they can tell how far away they are. Here we're only at 9.3 miles and we already got 10,000th of a second. So let us now see how that oscilloscope works. In order to really work with it, we have to understand something about it, and it's really quite simple. In fact, here's a sort of version, a stick version of it. Here's a piece of wood pivoted down here. But it doesn't fall down to the ground because you see how it's supported here?
Rubber bands there.
Rubber bands holding it up. One here, one here, one here, and one here. Now, notice that because it's pivoted back here, any motion here is transferred up. There's quite a big motion up here.
Right.
In the end here is a little tiny light bulb. In fact, I'll turn it on down here. And I can put a little screen there. In fact, let me turn this over here so you can see it now. See, there's the light in the...
Yeah.
Now, pretend that you can't see my hands back here, because I'm going to put pressure or forces of some kind on the stick back here where the rubber bands are, and you just look at the light and you tell me what kind of forces I'm putting on. Let me turn the light down a bit. Okay? Now, just look at the light and tell me, what am I doing, what kind of force, and in what direction am I putting now?
Well, your hair must be on top and pushing on the stick down.
Why?
Because the light goes
The light went down, didn't it? Now what happened? Took it off.
That's right. Standing still.
Standing still. What happens now?
Well, you moved it to the right, so you must be pushing on the left side.
Right. Here. Now let me try the other side.
Well, it moves to the left, and so you're pushing on the right side.
In fact, you can even tell this now, can't you?
So you're pushing...
Up and down, right?
Yeah,
and
up
putting
and down.
a series of pulses. Okay, well, this is exactly how radar, or how the oscilloscope works. This stick here represents a beam of electrons coming out from a gun here.
Electron gun?
Electron gun, yeah, like in the back of the television set. So this is a beam of electrons, and they hit a special kind of glass coated with a phosphorescent material so that when it hits it, it glows.
Like the light.
Like the light, yes. And these things back here now are plates where we can put various forces on it. In fact, let's see the same thing now, but on a real oscilloscope. There it is right here. See that little dot?
Yeah.
Okay.
That's
the beam of electrons hitting this phosphor-type material on the ends of the plate. In fact, if we turn this now, we can see that... See back here?
Oh, yes,
Here's the tube, and there's where the mechanism is.
Come out.
The electrons come right back there. Now, in fact, I've got another tube right here. See, this fits in here like this. Just like that, see? This part here is this part here. This is a little bigger one. Let's take a look at this now and see if I can show you. Right here, I'll use my pencil so you can see. Right back here is where the electrons come from. This is this section right in here. Now, here they're speeded up. And right here are two plates. See those two plates? As the electrons go zooming through here, we can do things to these plates to move them to one side or the other, just like I did with the rubber bands. That's one direction, right? That would correspond to two rubber bands. Now look up here at the end.
Hey, two big ones.
Yeah, see there are two bigger plates right here? Well, those two big plates now represent two other rubber bands. And as the electrons go through here, we can put various forces on these plates and deflect them again.
So you mean like the rubber bands, you can change it,
Right.
where the electrons go?
Right. The electrons, if we had nothing on these plates at all, would go zoom right straight.
Straight.
And now we can put various forces on here. Now, let me see if I can play a little guessing game with you.
Okay.
If you were to figure out what kind of forces you could put here on these plates to make the electron beam go over, what would you do? In other words, what affects electrons?
Well, I guess other electrons.
Other electrons. Where are you going to get a supply of electrons?
Well, from the house.
Around the house? Where do you mean?
From the outlet.
Oh, you mean electricity?
Yes,
That's right.
electricity.
How about the easiest one is to just scrape your feet across the rug and touch somebody, you know, on a good
static
winter day.
electricity.
Static electricity. In fact, that's what this machine is, you know?
Oh, yes.
Static electricity machine, you turn it on, down there, see that switch? Right there.
See. Should I turn it
Yeah,
on?
go ahead, turn it on. And remember, you can put your finger here and get sparks from it? Well, look what it's doing to the beam of electrons.
It's making it move.
Yes.
So I guess static electricity.
Certainly, the electrons being shot out from here affect these electrons and push them away. In fact, what'll happen if I take it over to the other side?
That's all right. Well, would it go, would it come over here, the light? Would it move over?
Yeah?
So static electricity really
Static
does.
electricity, effectively. Okay, you want to turn that switch on?
Okay.
Now, you want to put it back over there? You mentioned electricity around the house. What kind of electricity do you want?
Oh, battery.
It's a battery. Yes, that's direct current.
Direct
Let's try hooking that up on it. Here, now you take that one and touch the... wait a minute, what happened here? Now, that's... Did you turn that other switch on? Pull it out?
Yeah.
Check it over there, will you? Let's see if it came out. No. Well, I don't know what happened to the beam. Well, gone.
Not a
Well, perhaps it did. Well, anyway, to go on to explain what would happen here. When we have the beam up here, and you put a direct current on one of these plates over here, the beam is deflected off to one side. Now, what would happen if we turned the battery around and put the current going the other way?
Well, if it on one side, and you turn it around, it would go on the other side.
On the other side, that's right. How about what would happen if we put alternating current?
Alternating current?
Yeah.
Well, We'd go back and forth, actually, wouldn't it? Because at first it would go one side and then to the other side.
Now, this is the way this scope works, and this is for demonstration purposes. Let's go and do that same thing over there on that oscilloscope that I was working with when you came in, and show how we can make that dot move around. Let's set it up for a dot. There's the dot, see it?
Right. That's the beam of electrons.
That's the beam of electrons going up here and hitting the screen. Now, I put a current on here, an alternating current, right? You can tell because it first moves one way and then the other. This is 1 cycle per second. What? 1, 2, 3, 4, 5. One change of direction every second. Now I'll go to 2. Watch.
It goes twice as fast.
Yeah.
1, 2, 1.
3, 4, 5, 6. Pretty soon it's going to be it's hard to keep track of it. It's going to go so fast, right?
Right.
Let's go back to the 1 now. There's
That's
1. Now, I'm putting that alternating current on one of those sets of plates. Now here is another generator of electricity over here, and I can put the signal on the other set of plates from over here. In fact, watch, I'll turn the volume up here now, and you watch. See?
Oh, it
now, as this dot is going back and forth, I'm making it vibrate in this direction 35 times every second.
Oh, so you have it going in 2 directions.
2 directions at once. Now, what'll happen if I move this to 2?
2? Well, this goes 2 this
2
way.
times, and this is 35 still. Okay, and 3, 4, 5, 6.
Is that how you got the different patterns?
That's how I got the different patterns. Watch. Let me change this over to the other scale. I'll put this on 10. There's 10, 20, 30. There's 40.
40?
You move that dial over there until you get 40 over there and see what kind of a figure you get.
Okay. It looks like...
Come on, get it adjusted very carefully. You should be able to get it to stop. Now, you see, if we have a current going this direction and then that direction, and at the same time we have one going this direction and this direction, we should end up with a circle, shouldn't we?
Circle.
And that's the kind of circle we get.
Is that what you...
Go ahead.
You had one of that, I think, at the beginning, when you first saw it.
Now try moving that and see what very interesting patterns you can get.
Oh, it's spinning.
Yeah.
Well, that's interesting.
Now scientists can study this and by counting the number of loops, and they can find out what the combination of various frequencies are. These figures are called Lissajous figures after the man who first described them a long time ago in investigating sound.
They look like it's in a 3-dimensional.
Yes, it looks like it's a bracelet spinning around one way. Or some people see it one way and some people see it the other. Turn that back to 35 over there, or about 30 or 40, someplace, you know, down in here. Let me try varying this one now. That's an interesting one.
It's like an hourglass.
Yeah. Now let me switch back over here. I'm now in hundreds. Now adjust that one around and see if we can get that spring to stop going up and down.
There.
Yeah. Now it's going around this direction, you see? It was going around this way before. There's a double one, see it?
Oh, yes. They're interesting.
Aren't they? Here's my Scotch plaid.
Now I can see what you mean.
Now scientists then, you see, use this to study simple things like this. Also things like this. What? Listen. That's what you were...
That's right.
You
That's what
thought
I
about
usually do.
oscilloscope, right?
But it's usually going the other way.
Well, you see, I now have the signal coming from the phonograph going in this direction, and I have the signal from this going in this direction. So I just reverse them.
Mm.
Okay, but now we have to use this idea to solve our problem of this small interval of time from the time you throw the switch until the light bulb comes on. And you said instantaneous.
That's right.
Well, let's see a different kind of oscilloscope now. It works on the same principle, but has a couple of refinements in it. Over here it is. See, here's the oscilloscope screen. Now, it's a big one with lots of dials on it. See that little dot right there?
Yes.
Well, let me check the intensity. See, I can make it brighter or dimmer by adjusting this. Now, this is not sweeping, notice. There's just a little dot there.
It's not moving.
It's not moving at all. This scope can be set up in such a way so that when some kind of an impulse is set into it, it now sweeps. Watch.
And it goes across the screen.
And it goes across, it sweeps now once for every impulse that comes in it. And you can vary the sensitivity so that it'll sweep at whatever voltage you decide to apply on it. You can also change the time that it uses to sweep across here by going very slow or very fast. See? Here it goes so fast it's all one line, just like when we had one cycle before, remember?
That's right.
Okay, now let's leave it at this. Now, if instead of using the internal thing to pulse it off here, we, let me turn the intensity up so I can see where I am here. Now, here's a switch. And when I flick the switch, a little current's going to go through the wire. I can adjust this so that that current going through the wire triggers this. Watch. See it?
Oh, it jumps up.
It jumps up. Now, that means that the instant the switch is closed, this beam will start going across. However, this switch is connected to these wires over here. It goes back over here, and here's a light bulb. So the light will go on, but it's going to take a while for the filament to heat up, isn't it? When it gets bright, light is going to be sent out, and up here is a photoelectric cell. So this is not going to send out any signal until the light's bright.
That's right.
The signal from the photoelectric cell is piped back over here and goes into the scope and is set so that it'll deflect it.
Oh, you mean with the switch, it just makes it trigger it to make it
triggers.
go, and then the light makes it
It makes it go up. So now all we have to do is turn on the light and find out when does it get to brilliance. Now notice, here's where the light is when it's bright, up here.
Right.
And here's where the light is when it's off, down here. Now, you tell me how long does it take for the light to go up to here to get to brilliance. Each one of these little squares that you see on here is 20 milliseconds.
Millisecond?
Yeah, a millisecond now is 1,000th of a second.
Wow.
1,000th of a second. And each one of these is 20
each
milliseconds,
box.
each box. So now let's try it.
It's sweeping.
Yes, it's sweeping. How long did it take to get up to brilliance?
Well, it looks...
Where? Put your finger on the line that you think it gets up to. Just about that one right there.
The middle one.
The middle one. Okay, how many lines is it over from the beginning until the end?
That's one, two, three, four.
4.
So that's 80 milliseconds.
80 milliseconds. Take off a 0 from the 8 and the 1,000.
800.
Yeah, you got 800ths of a second.
So there is a difference in time when I just
Quite
turn
a
the
bit.
lights.
Remember that. About
Light switch.
800ths of a second, you can tell somebody it's 80 milliseconds in sound.
They won't know what it is.
Quite a long time by scientific standards. Now notice that these go zing over here real fast.
That's right.
That it's hard to measure them. You have to do several of them. And what happens if we're only going to get one pulse?
One?
Yeah, then what do we do? Well, they've rigged up a thing that you can put a camera right over here and take a picture of it.
Camera?
In fact, let's do that, and let's make another test of some short interval sort of phenomenon. You know, when you put a flash bulb in your camera and fire it, it seems like a very quick flash.
Yeah.
And an electronic flash is also very fast. Let's compare the two.
You mean
How
the
fast?
difference?
Yes, there's quite a difference. In fact, here's how we can compare it. Here's an electronic flash. And now, whenever we push this switch right here, the electronic flash is going to fire, and the impulse is going to go up into this photocell and send it back over here, and we should get a trace. See it?
Oh, yes.
Yeah, but it was so fast it disappeared, didn't it? It has to wait a little while for this to warm up before we can do it again. So now let's set up a camera so we can take a picture of that. And here it is.
It's a big one.
Now I have to open the shutter, fire off the electronic flash, and then close the shutter, and automatically we'll expose the light, on the picture. So let's try it. Okay, now we have the electronic flash there. Now on the same picture, let's put the flash bulb.
You're going to do the same thing again?
I'll do the same thing this time, but put a flash bulb in it. So we can put both of them on the same picture, right?
I see, and you can compare the
You can
two.
compare them right on the same picture. So let's try this one. Okay, now. This kind of film takes 10 seconds to develop, and we can actually see the result. The point is, we could make individual tests and do a lot of electronic flashes, then we could do a lot of flash bulbs, and we'd know how long roughly each one.
You can keep a record.
No, so we could keep a record of it. Put the time, the date, everything else that we...
Did it come out?
Well, you'll see. I wanted to get this off of here so we could see it on the scope. Ugh. Put it on so tight I can't get my finger in there.
You're going to show me the picture?
Uh-huh. I'll show you the picture.
Oh, it came out nice.
Now, from previous tests, I know that the electronic flash is much shorter duration than the flash bulb. In fact, this is 20 milliseconds for each line again. See, here's where it started.
Yeah.
Here the flash went off, and it took only what?
One? Less than
20 milliseconds. Yeah, well, not maybe that quite, but less than that. Notice the flash bulb is 1, 2, 3, 4, or 3, 20-second, or 80 milliseconds, or 60 milliseconds about. So you can see you can put your permanent records down here, time, date, and all the rest of it, and make all kinds of measurements using this kind of scope.
So there is a big difference.
So there's a big difference between the two. In fact, scientists use this all the time to check that kind of short interval. Well, now, you remember that radar problem?
Yeah.
Down to 10,000ths of a second, you know, all this kind of stuff. Well, it's pretty hard to set that up here because we don't have those kind of distances, but we could use something in the place of light or radio. We could use sound, couldn't we?
Sound?
Yes, we could use sound in place of it. In fact, let's set it up and see if we can time the interval between when the sound hits this microphone. See, here's a little microphone on a stand. And here's going to be our sound source, a metronome.
Oh, yes.
Now, I can get it started so that it sends out a bang, 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 bang like that. Every time the sound from this thing goes into the microphone, a little electric current is generated. That's how a microphone works.
So to start.
Yeah. So we send that down over here, and we'll put it to pulse the scope. See, now every time the this thing beats up here, we get a beat. We're also getting some other beats in here. Now, did you notice those other things up there, those jagged lines? Well, here's what's happening. The sound, when it hits this microphone, is sending that line across. In fact, now, let me turn this one off over here, you'll see. Here?
That's the regular sound.
That's the regular sound coming from here and triggering the scope. However, it takes longer for the sound to go to this microphone than it does to go to this microphone way over here. There's what? 2 feet difference.
Yeah.
In other words, what we are going to do now is time the interval between when the sound hits this microphone and when it hits this microphone.
But it's such a short distance.
2 feet. And you
How
know,
can it be such a
sound, you know what speed sound moves at? 1,100 feet per second.
Oh, yes, that's right.
So 1 second, it's going to go 1,100 feet, you know, way, way off.
Yeah.
Fifth of a mile.
So it has to be fractional part of a second.
Right. Well, we still have this set at the same scale, 20 milliseconds for each one of these little divisions here. So now, when we set this up, the start here is going to be the beginning of our time interval. And you can now count the number of spaces that it'll take for the sound to come from that microphone to come in here and also disturb that line.
You make it move?
Yeah, we're going to make it move up and down, just like we did with the light and just like we did with the sound or the music over there. In fact, watch. There it is, this microphone all by itself, just pulsing. Now I'm going to turn on that other microphone over there, and you watch what it... We can't talk because we'll pick up the impulses over there. Now listen.
Okay.
Okay, how many is it?
1, 2.
About there.
It's about 2.
About 40 milliseconds.
So that's the difference.
That's the difference. 40 milliseconds is the time it takes for the sound to go from this microphone to that microphone. Now, if this is true, what I should be able to do is move that microphone over there, and what should happen to that line? Should it go this way or this way?
It should get longer.
This distance should go out here. All right, let's try it. You watch it now. keep track of now, where is it now? Remember, we can't talk because our voice goes on that track right there. Now watch.
Is
that 2? Okay, now watch. Okay, now watch. When I talk, you'll see my voice on that thing. Now, when I be quiet, you tell me how far away is the second microphone in terms of time.
It's about here. It's about the middle one. So that's 1, 2, 3, about 4.
It's now a total of 4 from the beginning?
Yes, not from the very first.
How far is it from the very beginning?
5.
5, and now where was our original? I'll move it back.
No, it's 2.
2. So the difference between the 2 positions in terms of distance here was what? 3 of these spaces?
That's right.
So that's, you see, we could calibrate this now. Instead of having this in milliseconds, we could have that in feet.
Yes, you can tell. That's how the radar
works. That's it. That's the exact.
Oh, and they can tell how far away.
Right.
So,
now, in this case, we're timing at intervals of 20 milliseconds, but by adjusting this, I'm now stretching that original thing out way out so that you can time now to billionth of a second. Billionth of a second with it.
Wow.
Okay, there it is slowly. See it? Here, let me get around there.
Okay.
I can turn this off and get back to the other one. Now, when you first came in, you thought it was amazing to be able to time the time that the light switch went on. And how do we do it? What is the instrument called?
Well, it's the oscilloscope.
Now, can you tell me briefly how an oscilloscope works?
Well, the oscilloscope sends off shoots off some electrons, and it's put onto a screen, and then we deflect it by using electricity or static electricity.
Yeah, some kind of electrical charge most of the time. Yeah.
That's right. And you can move it and deflect it.
Well, you see,
you can see the difference in time.
You can also use it to measure anything that you can change into electricity. You can change time into electricity, can't you?
Yes.
You can change by, we just did that, didn't we?
That's right.
How about sound?
Sound, you can
certainly change that into electricity, yes. In fact, practically anything you can think of, you can turn into an electrical signal of some kind because you can have it triggered and then you can put it on the scope and study it. And if you ever go through a research laboratory, like I have many times, you see an oscilloscope in every one of the scientists' and engineers' office that are almost like typewriters.
Typewriters?
Yeah,
automatic?
Well, they mean they're so common because they're such a useful tool to science. And when somebody asks you, how long does it take for the light to go on after you throw the switch, how many seconds are you going to say?
Well, I'll say about 1/10 of a second.
But if you want to be very exact, according to the measurements we've made, you can say what?
100.
No, I think it was 80.
Oh, 80 milliseconds.
80 milliseconds. Well, let's try. I've got it set up. Let's see.
Watch Mr. Wizard is presented each week at this time by the Public Affairs Department of the NBC Television Network in cooperation with New York University.